All right, hi year 11s, this is Mr. Lim again, and this is our last video about changes in conditions, and it's about surface area, so let's get started. Okay, so we're going to be learning about changes to surface to area to volume ratio. Okay, so surface area to volume ratio can be referred to as that, the SA colon V. All right, so we're going to describe what it is. Okay, we're going to describe how it changes collision theory, predict changes, use diagrams, and describe how the surface area to volume ratio can affect catalysts as well. All right, so let's move on. What is surface area to volume ratio? Substance's surface area to volume ratio is how much surface area there is exposed to the reaction compared to its volume. Okay, so it's about how much is exposed. Gases have the highest surface area to volume ratio because they are all spread out. Generally only referred to in terms of solids and their shapes, and you can say things with high surface area are flat sheets, small pellets, or even really small granules or powdered substances. But substances with a low surface area to volume ratio are large spheres or large blocks of stuff. Okay, so let's go show what that is. Okay, so changes to surface area to volume ratio change the proportion of particles exposed and available for reaction. Okay, and this changes the frequency of collisions. Okay, so let's start drawing some stuff out. So imagine I have a block of reactants here. Okay, a block of reactants here. Okay, the only ones that can react are the ones on the outside. The reason for that is that, remember, you have to have a collision for a reaction to occur. If these ones on the inside, they have no way to collide with the other reactants on the outside. So as the reactants on the outside are coming in to collide, they'll collide only with the outside ones and not the inside ones. Okay, so as a proportion there, I've got 25 particles. Out of those 25, 5, 10, 16 are exposed, right? And then 9 of them are not. Okay. However, if I was to take those same 25 particles and split them up into 5 sheets of 1, okay, so 1 sheet, 2 sheet, 3 sheets, 4 sheets, and 5 sheets. So 5 skinny sheets instead of 1 big block. All of these are available to react as particles collide into them. Okay, so because you've changed the way that they are arranged, you are now increasing the frequency of collisions. Okay, because now out of those 25, all of them are available to react because they're all exposed to the other reactant, and the other reactant can bump into them at any given time. Okay, so you are changing the frequency of collisions and thus the frequency of successful collisions by exposing more or less particles. Okay, so can you predict the changes to rate of reaction due to the surface area to volume ratio? Okay, so the relationship is proportional. So as the surface area to volume ratio goes up, so higher surface area to volume ratios means smaller things, skinnier things, the rate of reaction will also go up. Okay, that's nice and easy. Okay, we can show that on an energy distribution graph by showing the particles with sufficient energy that are exposed as a proportion of the particles with sufficient energy. So what do I mean? Okay, here's our Maxwell-Boltzmann distribution graph. Okay, here's our activation energy. I'm going to move it down further here. Okay, so these are the particles which have sufficient energy to react. But not all of those particles are on the surface. Maybe only some of them are on the surface. So out of those particles, out of all of that red area, only maybe these particles are on the surface. Okay, so particles at surface. So out of the particles that are have sufficient energy, some of them will have sufficient energy but not be exposed. Okay, so those ones there have sufficient energy but are not exposed, and so therefore they can't react. So only those particles at the surface can react, and so you can show that as a proportion. How would you then show that there is I don't know how I'm going to do this. How would you then show that you've changed the surface area to volume ratio and there is now more particles that can react? Okay, so let's do again this activation energy here. Okay, so this might represent, what do you think, if you have a high or low surface area to volume ratio? This might represent a low surface area to volume ratio, which means that a lot of them are not exposed to the surface, right? But something like this could represent a higher surface area to volume ratio, like you've turned it from one big block into lots of little blocks, okay? And so that can be the higher surface area to volume ratio, okay? And so therefore now there's a greater area underneath the curve that can react because they have sufficient energy and they're exposed. And so therefore their reaction will go faster. Okay. Finally, catalysts also need to be exposed to the reactants. And so therefore generally catalysts, they have a high surface area as well to expose more of the catalyst to the reactants. So therefore you generally find them in things like wire meshes or flat sheets or something like that. So that, or even nano-sized materials, okay, so that they can be exposed to as many particles as possible and therefore make the biggest difference. All right, and that's it for changes in conditions. Soon we move on to new stuff.